Hi everyone, before I start this video, make sure that you're a part of my Discord server by joining the link in the description box below. And in this video, we'll be going over A-Level Mathematics, May-June 2023, Paper 5-3. So this is Paper 5, Probability and Statistics 1, and the total time limit for this paper is 1 hour and 15 minutes. So in this video as well, we'll be attempting to complete this paper within 1 hour and 15 minutes. So without any further delay, let's get started. For the first question, two fair coins are thrown at the same time repeatedly until a pair of heads is obtained. So pair of heads means we just require two heads repeatedly, and the number of throws taken is denoted by the random variable x. Okay, now we need to state the value of expectation of x. So clearly this is a case of geometric distribution because we're doing the same thing repeatedly until the desired outcome is obtained, right? And the desired outcome in this case is a pair of heads repeatedly. So let's figure out the probability of getting heads repeatedly. That's a pair of heads. So the probability of getting one head from a fair coin is 1 by 2. And we're considering two heads, so that's multiplied by 1 by 2. This gives the desired probability to be of 1 by 4. So we can say that in this case, x follows a geometric distribution where the probability of the desired outcome is 1 by 4. Now always remember that for geometric distribution, the mean or the expectation of x is just going to be 1 by p. So we repeat the same process in this case as well. We've already calculated the probability to be of 1 by 4. So 1 by p would be 1 by 1 by 4. This gives the required mean to have the value of 4. That's all for the first part. Let's move towards the second one. We now need to find the probability that exactly 5 throws are required to obtain a pair of heads. So it means that for the first 4 throws, we did not obtain 2 heads, right? So it can be 2 tails or either 1 head and 1 tail. And on the 5th throw, we exactly got the desired outcome. We know that the probability of our desired outcome is 1 by 4, which means that the probability of not getting a pair of heads will be 3 by 4. So that's the probability for the first 4 throws. And for the 5th throw, the required probability is 1 by 4. We just multiply those 5 probabilities together. So 3 by 4 is 4 times. So we can just raise this to the power of 4 and multiply it by the probability of obtaining a pair of heads on exactly the 5th throw, which is 1 by 4. And this gives the required probability to be of 0.079. That's all for the second part. Let's move towards the next one. We now need to find the probability that fewer than 7 throws are required to obtain a pair of heads. So it just means that either we obtained it on the first throw or on the second throw or third, fourth, 5th, 6th, because we're considering fewer than 7 throws. Now for x equals to 1, we are obtaining a pair of heads on the first throw, and the probability of getting a pair of heads is 1 by 4. So that's all for x equals to 1. For x equals to 2, on the first throw, we did not obtain a pair of heads, and the probability of that outcome is 3 by 4. And then on the second throw, we obtained a pair of heads, and the probability is 1 by 4 in this case. That's all for x equals to 2. Now for x equals to 3, we did not obtain a pair of heads in the first 2 throws. So the probability will be 3 by 4 raised to the power of 2, because we're talking about 2 different throws in this case. And on the third throw, we got a pair of heads. That will be all for x equals to 3. Now for x equals to 4, we did not obtain a pair of heads for the first 3 throws. So that will be 3 by 4 raised to the power of 3 multiplied by the probability of obtaining a pair of head on the 4th throw. So 1 by 4. Then for our x equals to 5, that will be 3 by 4 raised to the power of 4, because we are not obtaining a pair of heads on the first 4 throws. Then we obtained a pair of heads on the 5th throw. And now for x equals to 6, that will be 3 by 4 raised to the power of 5, because we did not obtain a pair of heads in the first 5 throws. Then we obtained a pair of head on the 6th throw. So that's the required probability. Now the sum of these probabilities will give the desired probability of 0.822. That's all for the third part. Let's move towards the next one. Now for question number 2, Anil is a candidate in an election. He received 40% of the votes. A random sample of 120 voters is chosen. Now we need to use an approximation to find the probability that of the 120 voters, between 36 and 54 inclusive, voted for Anil. Okay, so in this case, we are approximating a normal distribution from the binomial distribution. Let us first list down the elements of our binomial distribution. In this case, we have a sample of 120 voters, so that's our n. Then we know that 40% of the voters voted for Anil, so that's the probability of voting for Anil, right? That will be 0.4. Now Q will be 1 minus 0.4, which is 0.6. So in this case, X follows a binomial distribution with n equals to 120 and P equals to 0.4. Now we need to use an approximation. Now for approximation, what we do is we just take the same mean for our normal distribution as the mean for our binomial distribution. And remember that our mean for normal distribution is denoted by mu, whereas the mean for the binomial distribution is NP. So that's 120 times 0.4, which results in a mean of 48. Now we repeat the same process for variance, which is denoted by sigma square for normal distribution. And for the binomial distribution, the formula for variance is NP cubed. So that's 120 times 0.4 times 0.6, which results in the value of 28.8. Now, after approximation, X follows a normal distribution with mean 48 and variance 28.8. Okay, now we need to figure out the probability that between 36 and 54 inclusive voted for Anil. So we can just write it down as probability of 36 is less or equal to X is less or equal to 54. And we include the equals to in this case because we are told that 36 and 54 are inclusive. Okay. And since this is a case for approximation, we always need to perform a continuity correction. Let us first do it for 36. So we have 36.5 and 35.5. Remember that we are looking for X greater or equals to 36, which means that it will also include 36 itself, right? So we have to start from 35.5. So probability of 35.5 is less than X is less than. Now let's perform the continuity correction for 54. So that's 54.5, 53.5. And in this case, we're looking for X less or equals to 54, which means that 54 itself is also included. So we have to start from 54.5. Okay, and now this is a normal distribution, right? So we need to standardize it, and the standardization process is X minus mean divided by standard deviation. So that in this case will be 35.5 minus the mean is 48 divided by the standard deviation will be root under variance 28.8 is less than Z is less than 54.5 minus 48 divided by root under 28.8. This gives probability negative 2.329 is less than Z is less than 1.211. Okay. Now let us draw our standard normal curve for this probability. So this is 0. We have negative 2.329. Then we have positive 1.212. We require this region. Right? Now in order to get this region, let's start with just the 1.211. Let's split these parts. So this is the first part we require. Now for the part in our negative region, let's flip the curve because our standard normal curve is symmetrical. So we can place 2.329 here and this area will be equal to this area. So we basically require the sum of these two probabilities, right? Now how can we figure this out is if we figure out the probability less than 1.211 and subtract this area, then we get the required area, right? And always remember the probability less than 0 is 0.5. So we can write the probability of this required area as probability of Z less than 1.211 minus 0.5. Now we do the same process for this area. We can first figure out the probability less than 2.329 and subtract this area, which is 0.5. So plus probability of Z less than 2.329 minus 0.5. Now for these probabilities, we'll have to refer to the formula table. In this case, we're looking for the probability less than 2.329 and 1.211. Okay, let's start with 2.329. So we have 2.3 right here. Second decimal place is 2. So 3.2 right here. And the third decimal place is 9. So that's 2. Now the required probability will be 0.9898 plus 0.0002, which will result in 0.9900. So for this one, the probability is 0.9900. We repeat the same process for 1.211. So we have 1.2, second decimal place is 1, and the third decimal place is 1 as well. So the required probability will be 0.8869 plus 0.0002, which is 0.8871. Okay, now we need to substitute these values into our question. So the probability of z less than 1.211 was 0.8871 minus 0.5, plus the probability of z less than 2.329 was 0.9900 minus 0.5. This gives a final probability of 0.8771. That's all for this one. Let's move towards the next part. For the third question, a random variable x takes the values 1, 2, 3, and 4. It is given that probability of x equals to x will be equal to k times x plus a, where k and a are constants. Given that probability of x equals to 4 will be equal to 3 times probability of x equals to 2, find the value of a as well as the value of k. Remember that we are looking for values of two different variables, right? Which means that we require at least two different equations. The first equation can be obtained from the given condition itself, and the second equation can be obtained by the sum of all of our probabilities, because the sum of all probabilities should always be equal to 1. Let us first start with the given criteria. So probability of x equals to 4 should be equal to 3 times probability of x equals to 2. Now if you substitute the value of x as 4 in this case, we get 4k, 4 plus a, will be equal to 3 times. Let us now substitute the value for 2. So 2k, 2 plus a. Okay, let's open the brackets. So that will be 16k plus 4ka will be equal to 3 times 2, 6 times 2, 12k, plus 3 times 2, 6 times 1, so 6ka. So 16k minus 12k will be equal to 6ka minus 4ka, right? That gives us 4k will be equal to 2ka. Now a in this case is just going to be 4k by 2k, which results in the value of 2. Okay, so now we have obtained the value of a. In order to obtain the value of k, we need to use the second equation, which is just the sum of our probabilities. So probability of x equals to 1 plus probability of x equals to 2 plus probability of x equals to 3 plus probability of x equals to 4 should be equal to 1, because that's the sum of the total probability. Now for x equals to 1, if we substitute the value for x here, we'll get k 1 plus a, which is 2. Now if we substitute the value for x equals to 2, that will be 2k, 2 plus the value for a is 2, plus probability of x equals to 3 will be 3k, 3 plus 2, and for x equals to 4, that will be 4k, 4 plus 2. This should be equal to 1. Okay, so that is just going to be 3k plus 2 plus 2 is 4, 4 times 2 is 8k, plus 3 plus 2 is 5, 5 times 3 is 15k, plus 4 plus 2 is 6, 6 times 4 is 24k. Should be equal to 1. So now 3 plus 8 plus 15 plus 24 will be equal to 50. So 50k will be equal to 1, which means that k is just going to be 1 by 50. And the value for a is 2. So that's all for the first part. Let's move towards the second one. We need to draw up the probability distribution table for x, giving the probabilities as numerical fractions. Okay, so we have x, probability of x equals to x. And the values for x in this case is 1, 2, 3, and 4. Now we just need to list the probabilities. Remember that probability of x equals to 1 is equal to 3k, and the value for k is 1 by 50. So the probability for x equals to 1 is just going to be 3 by 50. Then the probability for x equals to 2 was 8k. So if we substitute the value for k, that will be 8 by 50. Then for x equals to 3, that will be 15 by 50. And for x equals to 4, that will be 24 by 50. That's all for the second part. Let's move towards the next one. Given that expectation of x equals to 3.2, that is the value for mean, we need to find the variance of x. Remember that the formula for variance of x is expectation of x squared minus expectation of x whole squared. Now we already have the value for expectation of x. We need to calculate expectation of x squared. And the formula is summation of x squared multiplied by probability of x equals to x. What this means is from our probability distribution table, we square the values for x, then we multiply it to their corresponding probabilities, and we sum these values. Alright, and for expectation of x, that is still going to be 3.2 squared. So the first one will be 1 squared times its probability, which is 3 by 50. Then we have 2 squared multiplied by its probability, which is 8 by 50. Then we have 3 squared multiplied by the probability 15 by 50. And we have 4 squared multiplied by the probability 24 by 50. Minus 3.2 squared. Now this gives the required variance to have the value of 0.840. That's all for the third part. Let's move towards the next one. For the fourth question, the times taken in minutes to complete a cycle race by 19 cyclists from each of two clubs, the cheetahs and the panthers, are represented in the following back-to-back stem and leaf diagram. So n will be 19 for both cheetahs as well as panthers. And here we have the key. 791 means 97 minutes for cheetahs and 91 minutes for panthers. Okay, for the first part, we need to find the median and the interquartile range of the times of the cheetahs. Okay, so let's start with the median. That is just going to be n plus 1 by 2 item, right? And in this case is 19. So 19 plus 1 is 20. 20 by 2 is 10th. So we're looking for 10th item for cheetahs. Let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And according to our key, we know that 9 will mean 99 minutes. Okay, now let us calculate the interquartile range. Remember, the interquartile range is the difference between the upper quartile and the lower quartile. Upper quartile will be n plus 1 by 4 times 3 item. Lower quartile will be n plus 1 by 4th item. Now, again, n in this case is 19. So 19 plus 1 is 20. 20 by 4 is 5. 5 times 3 is 15. So we're looking for 15th item. Minus 19 plus 1 is 20. 20 by 4 is 5. Minus 5th item. Let's count. So this was 10th item. 11, 12, 13, 14, 15. So the 15th item is 106 minutes. Minus the 5th item is 1, 2, 3, 4, 5. 83 minutes. This gives the interquartile range to have the value of 23 minutes. That's all for the first part. Let's move towards the next one. Now the median and interquartile range for the panthers are 103 minutes and 14 minutes respectively. We need to make two comparisons between the times taken by the cheetahs and the times taken by the panthers. Okay, so remember that this is the times taken to complete a race, right? So we can compare the speed, which team was faster. And in order to figure that out, we can compare the median, because median is the middle values between our first observation or the lowest observation and the largest observation, right? So in this case, the median for cheetahs is 99 minutes, whereas the median for panthers is 103 minutes. Clearly, cheetahs are taking lower times as compared to the panthers, which means that we can say the times for cheetahs are faster than the times for panthers. That's our first observation. So times for cheetahs are faster than the times for panthers. Now, the second comparison can be made between our interquartile range. And remember, interquartile range is just the figure between our upper quartile and lower quartile. So what it does is it basically compares the ranges or the spread, right? The spread of the observation. So we can compare that. We can see that the spread for cheetahs is 23 minutes, whereas the spread for panther is 14 minutes. So we can say that the times for cheetahs are more spread as compared to the times for panthers. That will be our second observation. The times for cheetahs are more spread than the times for panthers. That's all for the second part. Let's move towards the next one. Another cyclist, Kenny, from the cheetahs also took part in the race. The mean time taken by 20 cyclists from the cheetahs was 99 minutes. We now need to find the time taken by Kenny to complete the race. Okay, remember that previously we only had 19 observation. Now we're talking about the mean of 20 cyclists. So the new cyclist is Kenny. So plus 19 plus 1, we have 20 observation, for which the mean value is 99 minutes. And we have been given the mean time, so let's utilize the formula. The formula for mean is summation of x divided by n, right? So summation of x just means that we are now adding up the times taken by each of the 20 cyclists. And that gives the mean of 99. Okay, now we can figure out the summation of the 19 cyclists from the back-to-back stem and leaf itself, right? And I think we're looking for cheetahs in this case as well. So let's figure out the sum of all these 19 observations. That will be 78 plus 79 plus 80 plus 82 plus 83 plus 87 plus 88 plus 97 plus 98 plus 99 plus 101 plus 103 plus 103 plus 105 plus 106 plus 112 plus 118 plus 119 plus 124. And that gives the sum of the time taken by these 19 cyclists to have the value of 1862. So we have 1862 plus we also need to add the time taken by Kenny. And we're trying to figure that out. Now the value of n in this case is 20 because we are taking the sum of 20 different observations, which means that 1862 plus time taken by Kenny will be equal to 99 times 20, which means that the time taken by Kenny will be 99 times 20 minus 1862, which gives the value of 118. So Kenny took 118 minutes to complete this race. That's all for the third part. Let's move towards the next one. Now for the fifth question, Jasmine throws two ordinary fair six-sided dice at the same time and notes the numbers on the uppermost faces. The events A and B are defined as follows. So event A is the sum of the two numbers is less than 6. Okay, then event B is the difference between the two numbers is at most 2. Now we need to determine whether or not the events A and B are independent. So events A and B will be independent if the probability of event A multiplied by the probability of event B is equal to the probability of event A and B, or A intersection B. So we're looking for 3 different probabilities in this case. And remember, in this question we're talking about 2 ordinary fair six-sided dice, and the scores or the numbers on the uppermost faces will be noted for both events A and B. In such cases, I find it easier to solve the question if I prepare the distribution table itself. Let's say this is dice 1, this is dice 2, 1, 2, 3, 4, 5, 6. These are the possible scores. Now let us first look at event A. For event A, we require the sum of 2 numbers, right? So if it's 1 and 1, the sum is 2. 2 and 1 is 3, 3 and 1 is 4, 4 and 1 is 5, 5 and 1 is 6, 6 and 1 is 7. We repeat the same process for these values as well. So 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. These are the sum. And for event A, what we're looking for is the sum of two numbers less than 6. So less than 6 in this case is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And remember all of these possibilities, we have 6 times 6. So the total possibilities are 36, which means the probability of A is just going to be 10 out of 36. Because out of these 36 possibilities, 10 matches the criteria for event A. Now we prepare a similar table for event B as well. So 1, 2, 3, 4, 5, 6. And for event B, we're looking at the difference between the two numbers. So 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, 4 minus 1 is 3, 5 minus 1 is 4, 6 minus 1 is 5. We repeat the same process for the remaining values. So 2 minus 1, 1, 0, 1, 2, 3, 4, 2, 1, 0, 1, 2, 3, 3, 2, 1, 0, 1, 2, 4, 3, 2, 1, 0, 1, and 5, 4, 3, 2, 1, 0. Okay, remember we still have 6 times 6 possibilities, so the total possibilities will be 36. And for event B, we're looking for the difference between two numbers, at most 2. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now the probability for event B is just going to be 24 out of 36. And we also need to figure out the intersection of events A and B. Let's do that. The probability for event A as well as B. So we're looking for our probabilities in the same space now. Let's see here, 1 and 1 will give the criteria for event A as well as event B. So that's 1. Then we have 2, 3, 4, 5, 6, 7, and 8. The remaining won't match because the remaining matching criteria for event B won't match the criteria for event A, and the remaining matching criteria for event A won't match the criteria for event B. So the probability is just going to be 8 out of 36. Now let's calculate the value for probability A multiplied by probability of B. So that's 10 by 36 multiplied by 24 by 36. And this gives the probability of 5 by 27, which is clearly not equal to the probability for A intersection B, which is why events A and B are not independent. We have to write it down clearly. Events A and B are not independent. That's all for the first part. Let's move towards the second one. We now need to find the probability of B given probability of A dash, which is not A. So the formula for the given cases will be probability of B intersection not A divided by probability of not A. Let us first figure out the probability of not A. So we know that event A, the matching criteria are the circled values, which means that the remaining values are the criteria not matching event A, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So 26 out of 36. That's the probability of not A. 26 out of 36. Now for probability of B and not A. So probability of B are the circled ones, and the probability of not A are the cancelled ones. So we need to see which of these will match each other. So we have 1, then we have 2, 3, 4, 5, 6, 7, 8, and 9. Then we have 10, 11, 12, 13. So 10, 11, 12, 13, and 14, 15, 16. 14, 15, 16. We're basically matching the ones which do not meet the criteria for event A and the ones which meet the criteria for event B. And that will be 16 out of the 36 possibilities. So that's the probability for numerator. And this gives a final probability to be 16 by 26. That's all for the second part. Let's move towards the next one. Now for the sixth question, the mass of grapes sold per day by a large shop can be modeled by a normal distribution with mean 28 kg. So let us assume that the mass of grapes sold per day by a large shop is denoted by X. This means that X follows a normal distribution with mean 28 kg, and we do not know the value of our standard deviation in this case. On 10% of days less than 16 kg of grapes are sold, we need to find the standard deviation of the mass of grapes sold per day. We'll be using this criteria. So what we are given is less than 16 kgs. So probability of X less than 16 will be on 10% of the days. That's the probability. So 0.10. And remember, we are working with normal distribution, so we have to standardize it. So probability of Z less than 16 minus the mean of 28 divided by the standard deviation will be 0.10. That will be probability of Z less than negative 12 by sigma will be equal to 0.10. Now we can draw our standard normal curve. Clearly this value is negative, right? So it falls to the left side from 0, maybe somewhere around here. And this probability is 0.10. Now the table will only give us the probability less than a positive figure, so we can flip this diagram because the property of symmetricity, right? So negative 12 by sigma can be shown here as positive 12 by sigma. The probability of greater than this value will be equal to less than the negative value, so 0.10, which means that the probability of less than 12 by sigma will be 0.90. That's what we're looking for in this case. Now for this one, we need to refer back to our formula table. We're looking for the corresponding probability where Z is 0.90, and 0.90 is a standard figure, so that will be given in the below table right here. For probability 0.90, the Z value will be 1.282. Let's substitute this value into our question. So 12 by sigma will be equal to 1.282. And this will give the standard deviation to have the value of 12 by 1.282, which is 9.36. That's all for the first part. Let's move towards the next one. Now, the mass of grapes sold on any day is independent of the mass sold on any other day. 12 days are chosen at random. Find the probability that less than 16 kg of grapes are sold on more than 2 of these 12 days. Okay, so this now transforms into our binomial distribution because we are looking at 12 days. So that will be our n. The probability that we're looking for in this case is less than 16 kg. And this was given above right here to be of 0.10. So this can be modeled by variable y, and this is a binomial distribution. We have n equals to 12, p equals to 0.10. All right, and now the probability that we're looking for is more than 2 days. So that's probability of y more than 2, right? More than 2 in this case would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a lot. So rather than calculating the probabilities for these many numbers, what we can do is we can calculate the probability for 0, 1, 2, subtract it from the total probability of 1, so that the probability for the required numbers will be given. right? So we can write this down as 1 minus probability of y equals to 0, 1, 2. And remember, for binomial distribution, probability of y equals to r will be NCR, p to the power r, q to the power n minus r. So 1 minus, for r equals to 0, that will be 12C0, p 0.10 to the power 0, q will be 0.90 to the power 12. Then for y equals to 1, that will be 12C1, 0.10 to the power 1, 0.90 to the power 11, minus for y equals to 2, 12C2, 0.10 to the power 2, 0.90 to the power 10. Alright, and this will give the desired probability to be of 0.111. That's all for the second part. Let's move towards the third one. In a random sample of 365 days, on how many days would you expect the mass of grapes sold to be within 1.3 standard deviations of the mean? So we're looking for 1.3 standard deviations of mean, right? So we can directly convert this into a question for standard normal distribution. We can write this down as probability of z being within 1.3. So it can be from negative 1.3 to positive 1.3. Let's draw the standard normal curve for this one. So we have 0, we have negative 1.3, positive 1.3, and we're looking for this area. Now we can split this into two different areas. So one would be from 0 to 1.3 because of the symmetricity property, and another would be 0 to 1.3 again. So we're looking at the same area twice. We can draw this as 0 to 1.3. We're looking for this area but twice. So how can we figure this out is we can first figure out the probability less than 1.3, then subtract this area, so that's 0.5, then we get this area once. So we need to repeat the process twice in this case. So twice what we do is start with probability of z less than 1.3, then subtract 0.5, which is the area below 0. Now for this value we need to look at our table again, and the z we're looking for in this case is 1.3. So we have 1.3 right here. That's 0.9032. Let's substitute this value. So we have 2 times 0.9032 minus 0.5, and this gives the required probability of 0.806. And now this is only the first part, because we still have to figure out the expected days out of 365 days where this probability is met. And always remember, in order to calculate the expected number or expected days in this case, you have to multiply the given sample, which is 365 in this case, to the required probability criteria, which is 0.806. And this gives the value of 294.19. Since we're looking for expected days, we need to round it up. So 295. That's all for the third part. Let's move towards the next one. Now for this one, we need to find the number of different arrangements of the 10 letters in the word Casablanca in which the two C's are not together. So whenever we are trying to figure out the arrangements with something not together, what we can do is figure out the total arrangements and subtract the arrangements with the criteria not together. So in this case, the criteria not together is 2 C's. Now we subtract the arrangements with 2 C's together. Okay, so total arrangement will be of the 10 letters, so 10 factorial. Then we divide it by the repeated letters. So C is repeated twice, that will be 2 factorial. And A is repeated 4 times, so times 4 factorial. Now for arrangement with 2 C's together, we consider these 2 C's to be a single letter. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 letters. So now we're looking for the arrangement of 9 letters where A is repeated 4 times. And if we consider the arrangement of C itself, that will be 2 factorial divided by the repeated letters of C, which is again 2 factorial. This gives the required number of different arrangements to have the value of 60,480. That's all for the first part. Let's move towards the second one. We are now looking at the number of different arrangements of the 10 letters in the word Casablanca, which have an A at the beginning and A at the end, and exactly 3 letters between the two C's. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 letters. We have A at the beginning, A at the end. We require 3 letters between two C's. So the first possible position for the two C's will be here, and exactly 3 letters, so here. Or we can have C here and second C here, or we can have third C here and fourth C here, second C there, or we can have the first C here and the second C there. So we have 4 different positions for C, right? And the position for A is already fixed. We have considered the position for C as well. So the remaining letters will be 1, 2, 3, 4, 5, 6. We only have to consider the arrangement for the 6 remaining letters now. So that will be 6 factorial divided by the repeated letter will only be 2A, because for 2 of those A's, we've already figured out their position. We do not have to consider those again. So the repeated letters will only be 2 A's, and then we have to multiply it by the position for C, which is 4. This gives the required number of different arrangements to have the value of 1440. That's all for the second part. Let's move towards the next one. Now we need to find the number of different selections in which the 5 letters include at least 2 A's and at most 1 C. So we need to have at least 2A and at most 1 C. And we're looking for 5 selections. 1, 2, 3, 4, 5. Okay. So let's start with the minimum letters for both these criteria. So for A, we need to have a minimum of 2 A's. And for C, we can have a minimum of 0 C, right? So we have considered the selection from C and A. So from the remaining letters, that's 1, 2, 3, and 4. From the remaining 4 letters, we need to have 3 selections for this criteria. So that will be 4C3, right? Then, okay, let us first increase the criteria for A without changing the minimum criteria for C. And remember, we have a maximum of 4 A's. So we can at least have 3 A's or we can have 4 A's. In these cases, from the remaining 4 letters, we need to select 2, so 4C2. And for this one, we need to select 1, so 4C1. Now let's move the number of A's to its minimum, so that's 2 A's. And now let's increase the value for C. So maximum, it can be 1C. So we input 1C. Now from the remaining 4 letters, we need to select 2 letters. Now C cannot be increased further, but A can still be increased further. Let's do that. We can have 3 A's and 1 C, so that is 4C1. And we can have 4 A's and 1 C, so that's 4C0. Okay, so 4C3 is just going to be 4, 4C2 will be 6, 4C1 will be 4, 4C2 will be 6, 4C1 will be 4, 4C0 will be 1. Now we need to add these values in order to get the number of different selections. So that will be 4 plus 6 plus 4 plus 6 plus 4 plus 1, which results in 25. That's all for this part. And that's all for this paper as well. So if you found this video useful, make sure that you like the video and leave a comment below. And make sure you're subscribed to the channel and hit the bell icon so that you do not miss any of these videos in the future. Thank you.